I'd like to talk a little bit about our company. We do a lot of resource construction. We started in 1999 as a forestry consulting company and quickly brought in a construction component. And we do a lot of work with GRS, geosynthetic reinforced soil. So we do a lot of arches, walls, bridge abutments. And these are just some of the projects we've done over the last couple of years. What I'd like to draw your attention to today is a project, and there's a couple of case studies in front of you on the tables, and I encourage you to have a look at those a little bit later. One of those is this open water project that we're going to talk about. When you hit open water, is it the end of the road? And in this case, it wasn't possible to continue with conventional construction methods, and we were asked by Synovus to help solve this problem. They recognized that this wasn't business as usual. They needed to do something different. They wanted to get our perspective on it, and Rob and some of his guys earlier on pulled together some ideas and came up with something. The site had some constraints, and those were single-heading construction was required, so you only had access from one side of the open water. The goal was to maintain the wetland in terms of function and environmental values, and it needed to be done at a time that wasn't disrupting their other operations and at a competitive cost. So what we came up with in consideration of bridges, floating roads, we landed on using piles. And there's a long history of pile use. Started in Europe, and lots of foundations and footings, more recently embankments. And effectively the process is find some wood, drive it in the ground, and build something on top of it, like a road or a city. This is the my summer vacation portion of the presentation. And so last summer I went with my family to Venice, and I was quite interested to see the amount of piles and pile-supported structures there were throughout the city. This church was built almost 400 years ago after about a third of the population of Venice was wiped out by the plague, and there's 1.1 million piles supporting this. So their approach, drive piles, put a wooden platform on, and then put something on there like marble. So our approach is very similar, except we've left out the marble. The bell tower at St. Mark's Square there, in 1902 the thing tipped over, and when they went to rebuild it, they looked and they went, these piles seem like they're in good condition still. Let's continue to use them. And those piles were 1,000 years old. So we know it works, and we have some examples close to home that where we practice this, and we want to talk to you today about the project that we did in some open water. And you guys can name the wetland, but Rob's going to talk a little bit about the case study, go through a bit of a slideshow of the steps and procedures, and there'll be a really good opportunity to see it right from the way we saw it on day one to the way we left it. So, Rob.
So when we got to this is a plan view of the site. The open water areas are in gray. You can see the little dots there is the pile pattern that we had decided on. And this construction technique was using 2 abutments at either end and then 2 piers in the middle, joined by 3 small jump span bridges. And the total project area ended up being just over 50 meters in length. This is what the area looked like when we first arrived on site, when we showed up. And this was the road leading to the project site. And this was just recently completed within days of us arriving. This is built on 4 to 5 meters of peat, and they used their traditional road construction techniques in this area. And this actually involved 4 layers of swamp mats being put down, and they used 900 millimeter culverts staggered along the right-of-way, and then they stacked their traditional clay on top of that to bring it up to the road grade, and this is basically the finished road surface before they've put their road surfacing on. An interesting point on this is those 4 layers of mats per kilometer cost more than $2 million. So $2 million per kilometer for the mats for this type of construction. That's just the mats. Just the mats alone, no other construction costs. So we were on site for about 3 weeks, and that whole section of road there, mainly the end that's closest to us there in the photo, saddled more than 1/2 meter. So we started our construction using PVC, a plastic sheet pile, to contain our work area, and that's used instead of steel just because it's a little bit cheaper, but it's also easier to handle and manipulate on the ground itself. So we're just using that to contain our site. A local logging contractor that was logging in various locations in the area, we secured some logs from them, about 300 logs. They were 40 to 50 feet in diameter and had a tip diameter, or 40 to 50 feet in length and an 8 to 10 inch tip diameter. Those trees actually represented about 10% of the log decks that they were working out of. So it was a fairly high quality log for this area, but it did represent about 10% of the forest to create those. And we'll get into a couple points Lauren will get to later about what we're going to do about that. This is a sonic side grip vibratory hammer, and this is what we use to put the piles into the ground. Vibratory technology has been around for a long time, but this technology in this configuration with a high frequency vibration is actually quite new. And this unit is designed to apply a maximum of 50 tons of centrifugal force. The pile pattern is laid out using flags, some flagging, and then we start driving our piles, and this is the transition between the existing road, trying to get the approach to where we're going to start our structure. We generally start a whole bunch of piles that we can reach, and then we put the hammer actually on top of those with a thimble. We grab a thimble, put it on top of the pile, and drive them down to the design elevation. That allows us to put more pressure on the pile, and it also increases our speed. Any imperfections in heights and stuff, we trim those up to get them to the design elevation. And then we put a layer of swamp mats on top of that to cap the piles. The swamp mats are put in so that they're just at or below the water elevation, so that they remain wet and that they won't rot. And this provides the foundation for our GRS, geosynthetic reinforced soil. And it's basically compacted granular material and fabric in very tight spacing. A lot of people have heard of MSE. It's a lot further spacing, and this provides much more strength and provides the beam of support to carry our structure. We add a whaler on the outside and some anchors so that the footing acts as a unit, and you can see the GRS working there. This is a specific piece of equipment that we use. It's a track dumper. On single heading construction, this is a critical piece of equipment for us because it's basically an excavator undercarriage in the cab and the box, and you can just spin 360 degrees, so it allows us to dump on any angle that we want, and also you don't have any turnarounds. Just turn the cab and you drive straight back out. There we're continuing the GRS. Then we bring it up to the, continue with the GRS in thin layers of our compacted soil and fabric until we get up to our design elevation. But this is once we were finished the foundation, we started building the first pier. In order to reach the far side of the pier, we actually drove in 5 25-foot piles and just in a pattern and then set that stack of mats on it and walk the machine out so that we could reach the far side. That's 70,000 pounds of equipment and mats and the head and everything sitting on top of those piles, and it didn't move over the course of the construction, and it was put in just fresh. So we continue to put in build the center pier, and then we drive our piles into the middle of that pier. Once we do that, we actually draw the water down, the water table right down, pump that out, get our mats in, and then we continue with our GRS. We've got whalers again and ready rod holding the outsides of the pier to maintain its shape, and we continue building that up until the footings, the abutment and the pier are completed, and we begin putting our sheet pile bridges on. The sheets are put together, they get stitched together 2 at a time, and we just reach out and slide the tongue and the groove together from the other 2 sheets and just keep a continuous construction going across until the bridge is completed. Here you can see baffles are put into the middle of the structure and on the sides. This helps maintain the strength and the structure of the bridge while we're building it. The sheets are actually shipped to, we ship them in pairs, and they're nested together. And what we do is we just stack those all up, and all of the steel for this structure arrived to us on a single truck. If this was a concrete bridge deck, it would have taken 4 B trains to bring the same amount of material to us in the field. You can also see a little, there's a line of blue foam at the bottom that just evens out our foundation. If there happens to be any little imperfections, it just absorbs those and spreads the load of the bridge out. And the white foam on the end is used to transfer the entire weight of that bridge, because there's a void there so that the load is spread out over the entire foundation. In areas where we can't do compaction really well, we actually insert foam into those areas. EPS foam is very susceptible to hydrocarbons, and it'll disintegrate with hydrocarbons. So if there happen to be any leaks or vehicles leaking over time, we wrap the foam up with plastic to protect it. We finish filling that up in between using jumping jacks and plate compactors, and then we put in a set of, we put needle beams in there to distribute the load across all of the stringers. Then we start the second pier using exactly the same technique. We put the next bridge deck on, then we reach out, we do the final footing, put the next bridge in place to complete. We complete the GRS on top of the structure to tie everything together with our fabric and soil compacted again. And we use forms here to actually hold the shape and retain the fill so they don't go out onto the outside of the bridge structure themselves. We use these forms in all kinds of construction, doing arches, walls, and they're a common thing that we use. This is the finished road surface without the jersey barricades in place. And the structure itself is rated to a CL 800 loading, which is your typical highway loading. The road width itself, the total width was just around 12 meters, and once the barricades were on, there was a 9.5 meter running surface. The one thing I wanted to point out is Calvin Van Buskirk is not here today. He's with TerraTech Consulting. We work very closely with him, and he's an integral part of all these designs, and he's the guy that puts his seal on these things. And he's a very unique individual that, 99% of engineers, we would have a difficult time working with them to come up with this concept, and he has some very unique skill sets that we take advantage of.
So want to have a look at some next steps. And so here we showed the 2 types, the traditional hammer-driven piles in the diagram, and then the vibratory-driven head. And so what we need to do is establish a relationship. There's tons of data, lots of PhD theses have been done on drop hammer methods, And what we're trying to do is establish the relationship between the bearing capacity of the vibratory-driven piles and compare that with hammer-driven piles. So we've got an application that we're putting together. We'll submit to AITF, and we plan to test the method in various soil types, and then use different species of trees, diameters of trees, lengths of trees, and then look at the different frequency or the different pattern that we can use to try to get a relationship between, can we use more short piles and still get the same effect as fewer longer piles or bigger diameter piles. So essentially develop the playbook for pile-supported roads and structures to improve the cost effectiveness. So a bunch of the considerations for cost include the scale of the project. In particular, MOB and demob is a big part of that. This is some specialty equipment that we need to transport to site. Once we're there, the width of the road is a big driver on its cost. Single lane with pullouts, I think, are something that the industry needs to start looking at more and more, rather than having two-lane roads everywhere. You can manage the safety aspects of it through training, signage, radio procedures, and such. In addition, the depth of the fill and the availability of the fill is a cost driver. We've got a design for about 80 centimeters of fill on top of an access mat platform. So essentially have a continuous causeway of piles capped with access mat, 80 centimeters of soil, and then tapered off down to the mats. You don't need jersey barricades, and the fill, any fill will do. Sand is actually preferable because you can work in any weather. Depth of peat is a consideration. This technique that we have needs to be adapted if you get into really deep layers of peat, but we think with the locally available timber, we can do a 4 or 5 meter depths of peat using this technique. Other possibilities are to retrofit the existing roads with pile-supported culverts or bridges. So the idea would be to go to a grandfathered road that's already in place, that's causing some havoc on the wetland, excavate some of that material, drive some piles, put in one of these mega flow culverts. So Rob was just talking about TerraTech, Calvin Van Buskirk. He has a patent on the mega flow culvert. Essentially what it is it's a culvert with some triangular spacers, similar like the chocks that you would have to keep your RV from rolling somewhere, and then banded. And you can do that in 2 to 10 culverts in a row. So if you put that on an access mat, it's not going anywhere. You've established drainage that's going to work effectively for all time. So in summary, we think pile-supported roads is a minimization technique. We believe that hydrology is minimally impacted. It's possible to build a continuous causeway in peat up to 5 meters deep. There's a range of techniques available if you start to get outside of that range of peat depth. It's locally available timber pile. It uses locally available timber piles combined with GRS. You'll be able to exceed the CL 800 load rating. It's a reversible process, and there's restoration possibilities for existing roads. Now I do have a natural progression of a BMP as my conclusion, and I want to bring up these next slides. So this, of course, is the disbelief stage. Followed by outrage, brainstorming, and finally, the established best management practice.